Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing the Four Functions Theorem. So what is this? Well, first let's discuss correlation inequalities. So here's a natural question. How do we prove that two events are positively or negatively correlated? So what do I mean here? Other than actually doing out the calculations, there's a more general framework that will allow us to show this. So here's an example. Consider GNP, so the Erdős-Rényi random graph, GNP, where the edges are with probability P, and consider two events. So one is the event that GNP is actually Hamiltonian, so it has a spanning cycle. We'll call that H. And let P be the event where GNP is actually planar. So we get a planar graph. All right, so given these two events, it's natural to ask, how are these correlated? Are they positive? Are they negative? And what you might expect is negative correlation. What does that mean? That the probability that P intersect H is at most the product of the probabilities of H and P. So what do we mean there? We mean that somehow it's unlikely for a planar graph to be Hamiltonian in this random model. So it's unlikely to get both Hamiltonian and planar. So why is that? What's the intuition? Well, to be Hamiltonian, we somehow expect that we need to have many edges to actually get this to somewhat be dense in order to ensure Hamiltonicity. Where on the other hand, if you are dense, then you're unlikely to be planar. So that's the intuition I have, that somehow these properties are opposed. But now we actually want to set about to prove this. And there's many questions like this, where you think of different properties and you want to know, or do they have some kind of natural correlation? So let's talk a little bit about how these types of questions were solved, and we'll build up to the most general theorem here, which will be the Four Functions Theorem. Okay, so let's start with the case P equals a half, so where every edge is present, probability half, and that's actually implied by Kleitman's lemma from 1966. To state Kleitman's lemma, let me make a definition first. So we say that A is a monotonically decreasing family of subsets of n if for every A in script A and A prime subset of A, we have that A prime is in script A. So what do we mean there? Just that you're downward closed. So if you're in the set, then all of your subsets are also in this family. So that's monotonically decreasing. Of course, we could define increasing. We won't need it for today. But it would be similar, be upward closed. So then what's Kleitman's lemma? Well, you can phrase it as the following. It's that if A and B are two monotonically decreasing families of subsets of the 1 up to n, say the set 1 up to n, then the probability of A intersect B is at least the probability of A times the probability of B. So what do I mean by probability there? It might not be clear, but just as a proportion of all the possible subsets. So of the 2 to the n subsets, think of the probability as the number of them divided by 2 to the n, so the proportion. So we're saying that the proportion of A intersect B is actually more than expected just by producting their proportions. So somehow if we have monotonically decreasing families of sets, if they're both downward closed, then their intersection is likely. And that's somewhat believable. Somehow they're going in the same direction, and so we expect more than what just as if they were independent. So that's Kleitman's lemma. Of course, you could do the same where you'd have monotonically increasing families. Then again, you'd have this somewhat positive correlation. That follows from this just by taking the complements. And similarly, you could look to, if you have one increasing, one decreasing, then you get negative correlation. So that's Kleitman's lemma, where you look at these monotonically increasing or decreasing families of subsets. So how would you apply Kleitman's lemma? I claim that for the case P equal half, indeed we can show this negative correlation. So how does Kleitman's lemma imply the desired correlation? So here's what we need to prove. If P is a half, then the probability of P intersect H is at most this product. So you might want to go ahead and do it yourself and stop for a moment, but it's rather straightforward. So the trick is you consider the set n choose 2, so where n, that's from the set. So you think of all the pairs from 1 up to n, And this, of course, leads to the Ahlswede model. So you think of these as edges. So for every E, a subset of these pairs, you can create a graph G with vertices 1 up to n and edges being the set E. And then, given this family of subsets, we define two different families. So you first have the family script P, where you have the sets E, where GE is a planar graph. So you think of all the planar graphs you get. And the point is that this family, since deleting edges preserves planarity, is monotonically decreasing family. So if I have a planar graph with certain edges, then any subset, any subgraph you get would also be planar. And then it's not true for Hamiltonicity, but it's true for the complement. So if you do script H bar, where E sets E where G is not Hamiltonian, then since deleting edges preserves non-Hamiltonicity, we get that script H bar is monotonically decreasing as well. So if you delete edges, you're not going to magically get a Hamilton cycle. And then what do we do from there? Well, by Kleitman's lemma, these two families are positively correlated. So as a proportion. So the proportion of all of these sets, which is planar, and the proportion which are Hamiltonian, non-Hamiltonian, then end up with positive correlation. And those proportions are precisely the probabilities of the corresponding events in GNP, right? So in GNP, each of the subsets E is equally likely. And so indeed, these are the probabilities we're after for the case P equal half. And hence P and H are negatively correlated as desired, since P and H bar were positively correlated. So basically, it's a straightforward application of Kleitman's lemma when you realize you can pass to these subsets of the possible pairs and apply those as if they were families. So this works more generally with any kind of monotone properties. So if we have monotone properties or the complements of monotone properties, we can get these correlations for Gn1 half. What about GNP more generally? Well, for arbitrary P, the inequality follows from a generalization of Kleitman's. So here the generalization would be if I had two monotonically decreasing families of subsets of n, then the probability of A intersect B is at least the product of the probabilities, but I'm going to use a different measure of probability. So instead of each set being equally likely, which is what we get in Gn1 half, instead for every S subset of n, we get to find the probability PS to be P to the S times 1 minus P to the n minus S. So you could do a weighted sum, and then extend that, of course, to probabilities of families of sets by summing up. And so if you have this weighted measure, then it still holds as the claim. So this is generalizes Kleitman's lemma, and thus we could apply it for arbitrary GNP to get the desired result. Because again, we'd just be changing the weighting, but we'd still have monotonically decreasing families of subsets. All right, so that's what we have there. And this theorem is a special case, we should note, of the more general FKG inequality by Fortuyn, Castellan, and Ginebra. So we'll be studying in a bit the FKG inequality next time. But before we do that, we will actually concentrate, in order to prove it, on something even more general. So we'll note that there were many extensions and generalizations in this direction in the 1960s and 70s. So you saw 66's Kleitman's lemma. Harris had the first such one in 60. FKG came along in 71, and this was all generalized by Ahlswede-Daykin in 1978, who proved the very general Four Functions Theorem that implies them all. So we haven't stated the FKG inequality yet, but we will next time, and we'll derive it. We'll derive it from this very general Four Functions Theorem. So we'll do all that deriving next time, where we do FKG, we'll do Kleitman's, we'll do this theorem on this slide, we'll do all of that. But let's turn to the Four Functions Theorem, a very general theorem that implies all of these correlation type inequalities. So what is the Four Functions Theorem? Well, let R plus denote the non-negative real numbers, and then given a function from 2 to the n, so 2 to the n is the power set of n, it's standard notation there, so that's families, that's taking all of the sets and mapping them. So if we have a function on the subsets of n, and you have a family of sets A from the subset n, we would define phi of script A as the sum over phi of A, where A is in script A. So it's somewhat natural if we have a function on subsets, we can extend it to families just using linearity. And then given that notation, and also we're going to need a little more notation to state the four functions theorem. So given two families of sets, so A and B, we define A union B, this is in script, so script A union script B, to be A union B where A is in script A and B is in script B, and script A intersects script B to be A intersect B where A is in script A and B is in script B. So what's that doing? That's just some notation for we'll have script, if we have these families, we'll define their union to be take all the possible unions you get, their intersection to be take all the possible intersections we get. So that's a bit strange. So we're not intersecting the actual somewhat, sets. We're not viewing these as sets of sets and then intersecting those sets. We're actually doing something more, passing into the sets and looking at their intersections and their unions. So it's a bit strange, but just go with that. And now we can state the four functions theorem by Ahlswede-Daykin. Here's how it goes. There's four functions. So let alpha, beta, gamma, delta be functions on the sets. And then what do we do? Well, we're going to assume that if A and B are subsets of 1 up to n, so that's its hypo, that should be bar n, the inequality alpha A, beta B, at most gamma A union B, delta A intersect B holds. So this is somehow something like a submodular function. That would be true if you passed kind of to the logs, but it's for four different functions, so it's a bit weird, but we're saying if we have four functions, and if you take the product of alpha and beta, then that's at most the product of gamma and delta over the intersections and the unions. But that's the assumption. So we're assuming that this nice product inequality holds for all sets A and B, and then we will show that for all families of sets, script A and script B, that the same thing holds. So that alpha of script A and beta of script B is at most gamma of script A union script B, delta of script A intersects script B. So what's going on? We're somehow saying that if we know this inequality holds for individual sets, then if we instead look at families, and we're looking at the sum over the function for those families, and we're taking those products, that still holds. So that may seem obvious from afar, but it really is not. So we have to do some good work to prove this. So on to the proof. So we're going to fix our two families A and B, and now we're going to do some work. So in a general level, what's going to happen is we're going to refine, we're going to clean to make some assumptions about the functions in the families to kind of get down to one specific case. And then we're going to condition by induction on n, on the size of the set we're working with. So the n equal 1 case will be quite interesting, and then the n equal greater than equal 2 will do some reductions. So let's go through this. So what's our assumptions? You can assume without loss of generality that alpha A is 0 for every A that's not in script A. Why? So think about that. But you can actually make similar assumptions. You can assume beta of B is 0 for every B that's not in script B, that gamma is 0 for every C that's not in script A union script B, and that D is 0 for every D not in the intersection there. And why do all these true? So I'm going to pause and think for a moment, why can we do this if you look at the statement of the theorem? So the answer is that it does not change whether the desired inequality holds while still preserving the assumed condition. Right? So we only wanted to prove the inequality once you fix A and B for that specific A and B, the script A and the script B. And so setting the function outside of that won't change whether that desired inequality holds. But what it does is it kind of smooths up the process. It turns everything else off. And that's okay for the assumed conditions, because if you set A and B to be 0 outside, then of course the left-hand side will be 0, and that'll be fine. And then once you've done that, if you set the C's and D's to be 0, then it too will hold, because if it was going to come up, then we would have already set the appropriate A's and B's to be 0. And so it will also hold if we do all of that. Okay, so that's our first assumption. Set everything not interesting to 0. Then once you've done that, you can actually assume without loss of generality that A and B, these families, are all of the sets, since the desired inequality is the same. So And why is that? It's given the zero term. So you could look back at that inequality, but basically once we've set everything to zero, then if you added in all the extra terms, if you looked at what the inequality would be when A and B are all the sets, all the other possible terms would be zero by the assumptions above. So we may as well just enlarge our families to be everything. So that'll just simplify our analysis. So we do all this, we set it to be a zero out where anything uninteresting happens, and then we just enlarge our families, and now we have this nice world we live in where also script A union script B, and of course their intersection as well, are all the sets, since they're all the sets. And now we're ready to apply induction on n. So let's look at the hard case. So strangely, the hard case is when n is equal to 1. We actually have to do work there. So we're going to do some manipulation, and then we're going to reduce the larger n case to smaller values. So how does this work? So for each function phi in alpha, beta, gamma, delta, let's just define, this is just some shorthand because we'll have a lot of crazy equations, phi of 0 to be phi of the empty set, and phi of 1 to be phi of the full set 1, right? So n equal 1, we only have two subsets, the empty set or the whole set, and so we only have two values for each function. So then what are we really proving? Well, our assumptions are, if you go through the different possible sets for A and B, we have that alpha naught, B naught, beta naught is at most gamma naught, delta naught. The alpha 1, beta 0 is and alpha naught, alpha 0, beta 1 are at most gamma 1, delta 0, and the alpha 1, beta 1 is at most gamma 1, delta 1. So if you kind of go through that, so when A and B are empty, you get the first equation. When A and B are both 1, the whole set, you get the last equation. And then you get this weird mix in the middle where one's empty, one's not. But it's important to note you get gamma 1 and delta 0. So you never get gamma 0, delta 1, because while A and B seem symmetric, gamma is always the union and delta is always the intersection. So why do I mention that? Because we have to prove the inequality. And what's the inequality? If you work it out, we have the sum of alphas over everything, which is just alpha 0 plus alpha 1, times the sum of the betas, which is beta 0 plus beta 1. We have to show that's at most the product of the gammas and the deltas. And if you stared at that, if only we knew that that second equality was actually, that one of them was actually gamma 0 delta 1, then it'd be straightforward. The four different terms would just perfectly match up. But that's the issue. We don't know that. We know somehow the 0 terms match up, the 1 terms match up, but the mixed terms, we only have the inequality into 1, but not both. So why do I say all that? Well, this would mean it would follow from 1 to 3 if you actually knew that the term we get to use, gamma 1 delta 0, if you knew that was at most gamma 0 delta 1, then you'd actually just follow because you'd match up all the terms. And we'll point out that that certainly occurs if either gamma 1 is 0 or delta naught is 0. So if you're in the case that either gamma 1 is 0 or delta naught is 0, those middle terms don't really apply, and so everything just works out. So now we of course don't get to assume that, but we could assume that we're not in that case so that gamma 1 and delta naught are non-zero. And now is where the magic happens. So this is the beauty of the case, and really thinking about what it means for the n equal 1 shows it off, is somehow it seems reminiscent of what you expect because of the product of the terms, but the issue is they don't quite line up because we're matching, gamma's in charge of the unions and delta's in charge of the intersections, so it doesn't quite match up. But the idea is with some clever arithmetic we can show that it still works out if you make the assumption for all of these different terms. So let's go through that. So now that we know that gamma 1 and delta 0 are non-zero, we can learn more. So we can divide our first equation by delta 0 to get that gamma 0 is at least alpha 0 beta 0 over delta 0, and our third equation by gamma 1 to get that delta 1 is at least alpha 1 beta 1 over gamma 1. So we do a little trick there, which we've now picked up the non-zero fact, so we can afford to do that. And then our equation that we want to show can be replaced by the following. So we have the same left side with the product of the alphas and the betas. On the right side, though, we can now replace gamma naught with the smaller alpha 0, beta 0 over delta 0, and the delta 1 with alpha 1, beta 1 over gamma 1. So if we could only show this, we'd be done. And, well, you basically could work out. You multiply by gamma 1 delta 0, which is strictly positive, right? Everything here is always non-negative, and they're not 0, so we are allowed to do that. And then we get the following equations. We get gamma 1 delta 0 times the product of the alphas and the betas. And the right side clears up very nicely to alpha 0 beta 0 plus gamma 1 delta 0 and alpha 1 beta 1 plus gamma 1 delta 0. So you see we get the same gamma 1 delta 0 term in both by this manipulation. And now that looks a little scary, but actually they have a lot of similar terms that you can cancel and rearrange. So if you rearrange and cancel the like terms, what ends up happening, you get gamma 1 delta 0 minus alpha 0 beta 1, and gamma 1 delta 0 minus alpha 1 beta 0 is at least 0. That's the equation we want to show holds. So you could go through that. Basically, the terms with the alpha 1 beta 1s and the alpha 0 beta 0s end up canceling, and you rearrange and you unexpand and you get this inequality. And why do we know that inequality holds? Well, it holds since both terms are non-negative by 2. So we do a bit of magic. If we couldn't just do it because the gamma 1 delta 0 term was smaller than the other, then we can plug in, we can eliminate gamma 0 and delta 1, rearrange, get this product of these two terms, and they're both non-zero by our assumptions. So it's a nice use of all four inequalities to end up proving the full inequality. So that's the case n equal 1, so now we're done with that. And now we turn to the case when n is at least 2. So here, for every function and a subset of n minus 1, we'll define a new function phi prime. So phi prime will be phi of a plus phi of a union n. So what are we doing? We're somehow want to project the functions down a dimension. So what's the best way to do that? Well, you take the sum of a and a union n for subsets of n minus 1. So we kind of group up, we pair up each set with a and a union n, and we take the sum. So this will essentially project all the functions down a dimension by doing these pairs. And clearly for each function, the sum over all of them, so phi prime of 2 to the n minus 1, is the sum of the original over all the sets, so phi 2 to the n. And so now, given that, we'd be done. The inequality would follow by induction on alpha prime, beta prime, gamma prime, delta prime. So we could imply induction. We've gone down a dimension, and then it would just follow immediately if we could apply induction to these new functions. Because we'd be basically saying, oh, is the alpha prime over everything? Well, that's alpha over everything times the product of beta prime, which is beta over everything. Is that the same for gammas and deltas? Yes. But the issue is we need to assume that the inductive condition holds. We need to assume that for every a prime, b prime subset of n minus 1, that we actually have the condition. So not for families of sets, but just particular ones. That alpha prime, a prime, beta, b prime is at most gamma prime, delta prime. So sorry, there's a typo. That should be beta prime, of course. So we need to prove that this holds. And if you work it out, what does that mean? Well, just put in the definition from above. So really we're saying you have alpha a prime plus alpha a prime union n, and the same for betas where it's b prime and b prime union n, and then the same for gammas and deltas for their appropriate sets where we add n. So we get this problem. We have to show that for these two sets for alpha, these two sets for beta are at most somehow the corresponding sets for gamma and delta. But if you think about that, that follows from the n equal 1 case that we've already proved. So I won't do that detail. You can refer to Alon and Spencer for the quick details. But essentially, if you look at this problem, we have four functions which each take on one of two values. So essentially then what we can do is just think of these functions as one-dimensional functions. So, for alpha, you would think of a prime as its value for the empty set, and a prime union n as the value for the full set 1. You do the same for beta, the same for gamma, the same for delta. And if you do that, then the conditions on that one-dimensional set that we need for this thing to be true are actually hold from the conditions from the whole theorem. So basically, we've already done this arithmetic, this analysis on the n equal 1 case, and that concludes the proof. So that's very nice. Basically, in the n equal 1 case, there's a slight trick. We have somehow the wrong term, but we managed to fix it by using all four inequalities. And then more generally, you can just do a projection down one dimension, and then we also know that the condition holds in that projection because essentially that condition becomes the co-projection, the one-dimensional case for these sets. So a very lovely proof, not too complicated when you think of it from that perspective. All right, so now we're going to move on and finish up with some applications here. So next time we'll do the FKG inequality and Kleitman's lemma, but in order to go that way, let me just talk about lattices. So you might know a lattice is a poset in which every two elements, x and y, have a unique minimal upper bound, denoted x v y, called the join of x and y, and a unique maximal lower bound, denoted x wedge y, called the meet of x and y. So again, poset, so it's partially ordered sets, and where you get the transitivity properties, but we might have incomparable elements, and we have joins and meets. And then we say a lattice is distributive if for every x, y, and z, you can kind of do this distribution of these operations. So if you take the meet of x and y join z, then it's indeed ends up being the joins of x meet y and x meet z. And or equivalently, there's an alternate form where it's x join y meet z is x join y meet x join z. So that's just a definition, that's distributive lattices. And for two sets x and y, we could define x join y to be where you take all the possible joins, and x meet y to be all the possible meets, in the same way we had done for A and B sets when you're doing union and intersection. So lattices, it's a little bit more general than sets, where we are not just doing union and intersection, but actually really, if you assume distributive lattices, then that and families of sets are very much the same. So what do I mean? If L is a subset of is a set of subsets of n, and it's closed under union and intersection, then if you order it by inclusion, that will make it partially ordered, then it's a distributive lattice. So why is that? Well, namely the join of A and B would be the union, and the meet would be the intersection. So it's easy to see that our families of sets give rise to distributive lattices. Less obvious is that for every finite distributive lattice, L, that it's isomorphic to a sublattice of a family of sets. So why is this? Well, an element x and L is, we say, is join irreducible if whenever x is the join of y and z, then either x equals y or x equals z. So if you can't break x down into two actually somewhat smaller sets, then we say it's join irreducible. So if not, then you could actually reduce it to the join of two smaller things. But now if you take all the join irreducible sets and these elements in the lattice, and you let x1, xn be those join irreducible elements of L, you can get a mapping that's actually an isomorphism to a sublattice of 2 to the n. How do you do this? Well, for every x and L, you just put as its sets all I and n, where xi is is less than or equal to x. So you put all smaller join irreducible elements, and this creates sets. So that's what you do, and then the inverse of that procedure is x is equal to the join of all the xi. Now that's just a sketch, you'll note, because we didn't do all the work there. So you'd want to show that if you take that inverse, that it's actually an inverse, gives rise to x. You'd want to show that you preserve that basically joins and meets in the one become union and intersections in the other, and so on. But you can go ahead and do that for yourself. So basically, distributive lattices are like sublattices, i.e. families of sets that are closed under union and intersection. And so now we can derive the four-function theorem for lattices. So that little bit of work lets us do something a bit more general. Namely, if L is a finite distributive lattice, and I have four functions on the lattice to non-negative real numbers, and I know that for every x and y, the inequality that alpha x beta y is at most gamma with x join y and delta x meet y holds, then I can get this for actually sets of elements x and y more generally. So that's just straightforward because you'd apply it to the associated sublattice of sets. And now that actually has a rather nice application, because if you set all of these equal to 1, so if you just take functions that are equal to 1, then there's actually nothing to show in the condition. The first inequality would always hold. 1 times 1 would be at most 1 times 1. You can show then that if L is a finite distributive lattice, and if x and y are subsets of L, then what does that bottom inequality become? Well, if you have 1 for each value, then alpha x is just the size of x, beta y is just the size of y, and similarly we have x join y and x meet y. So this is quite a nice corollary already of the four-function theorem, that if you have this union intersection closed family of sets, then x times y is at most kind of the number of their unions and the numbers of their intersections. And that will lead us to our last application for the day, which is if script A is a subset of sets of n, set of subsets of n, then we define a set minus a, which is weird, but it's kind of like symmetric differencing. So we're going to define this to be f set minus f prime, where f and f prime are in A. So what is that? So a set minus a is all the kind of bits, right? So it's all the parts you can get, all these f minus f primes that you can possibly get from A. And now here's an interesting corollary of our last theorem there by Marika and Schonheim in '69. So of course, before the Four Functions Theorem, they were able to show that this A set minus A has size at least A. So that's quite an interesting fact, right? If I give you a set of subsets, we're saying that you could always get at least as many set minuses from them as the set itself. And you might want to pause and go ahead and prove this with the last theorem, but it's a little slick, so we'll just go ahead and do it. So what would you do? As your lattice, of course, you have all the sets. And now I have to have another family. So what do we do there? We're going to have script B be the complements of F. And now what do you get? The complements of A, so complement F where F is an A. So by the previous corollary applied to L, A, and B, we can find that script A times script B is at most A union B when scripts times script A intersect script B. So the number of A times the number of B is at most their possible unions and intersections. But think about that. Think about what that inequality says. Well, we're just doing complement, so A has the same size, script A has the same size as script B, right? For each set I get a complement. And then what is script A union script B or script A intersects script B? So script A union B there is I take a set in A and I union it with a set in the complement, which is the same thing. So if I pass to the complement, it's the same thing as doing set minuses. And same, right? If I take A intersect complement is set minusing, and vice versa. Even if you union, if you flip to their complements, it's taking the other. So each one gives rise to the possible set minuses, which means that those both are actually the same sets. They have the same size, and so you find that script A squared is at most A minus script A squared, right? So both of the terms above, both on the left become script A and the right becomes our A minus A. And of course, these are obviously non-negative, so you could take square root and you indeed determine that you get more set differences than the set itself, at least as many. And that concludes the proof. So that's all we're going to do for today. We talked about these correlation inequalities. So how do we actually show, like planarity and Hamiltonicity in G and P? How can we actually prove that they're positive or negatively correlated? So we saw Kleitman's lemma about monoconically decreasing families, which we'll prove next time, a generalization. And really we saw this most general form, this four-function theorem, and we proved it that if you have these four functions that for sets respect this inequality, then they do for families of sets. And that was very nice, and the proof went by splitting into cases. So the n=1 being the important one with some arithmetic, and the general being a reduction via projections and co-projections to smaller cases. So that's all for today. Until next time, see you then.